Hello everyone and welcome to this new abstract algebra video. Today we're going to talk about cycles once again, and we're going to prove some more results about cycles that will be quite important in our study of group theory. So the first one is that in the last video we talked about disjoint cycles, and also we talked about the order of a cycle, and we said that disjoint cycles commute. So now we're going to prove a fact about the order of cycles. In particular, that is that a cycle of length n has order n. So basically, if you have a cycle with alpha 1, actually let's call the cycle alpha, which is a1, a2, up to an, so it has length n. If you raise it to the nth power, you get the identity permutation, which we can denote as that we will denote as epsilon. So let's prove it. So in order to prove this fact, we need to show that basically n, which is the length of the cycle, is the smallest positive integer such that alpha is equal to the identity permutation. So in order to do so, you will start first by seeing that alpha raised to any other integer power less than n, and of course, well, supposing we're dealing with positive integers, so greater than 0, is not the identity. So how can we do that? Well, notice that we will just look at the first element, that is a1, and actually let's reindex it just to keep the notation consistent with the last videos, because and by looking at a0, well, we see that if we apply alpha k times to a0, what do we get? Well, a0 originally gets mapped to a1 if we apply alpha once, but if we apply alpha twice, then a0 gets mapped to a1, but a1 gets mapped to a2, and so we get that in total a0 gets mapped to a2. So in total, alpha of k, so alpha k times where k is less than n, yields that a0 gets mapped to ak. And notice that here we're supposing, of course, that k is not equal to a0, because of course in our cycle notation we do not repeat, we do not include stuff that are the same. And so from this we can deduce that alpha of k is not the identity permutation. Why? Well, because it does not fix an element, and that suffices to show that that is not the identity permutation. So yeah, and this is basically the first thing that we have derived. Then as a second step, we want to show that n is precisely the first positive integer for which alpha of n is the identity. And this will actually prove that n is the order. So how can we do that? So we'll first prove this, we could say, preliminary fact, and that is that alpha, our permutation to the k of an element a, say a of l, well, that is equal to a of l plus k mod n. And so this is the fact that we need to prove in order to show very easily that alpha to the n is the identity. So how can we prove this? Well, we will prove that by induction. So let's start with the base case. That will be k is equal to 1. So if I apply alpha once to a of l, well, suppose that a of l is here. So for example, somewhere around here. Well, then alpha of a of l will just be a of well, this is 1 here, so k is 1, so a of l plus 1. But notice all mod n. Why? Well, because if instead of a of l here in the middle, we had a of n, which is the last element of the cycle, then we will have that the next element is a of 0. But a of 0 is just, well, actually here n minus 1, if we're supposing this is an n cycle, be careful, okay, so that would be n minus 1 plus 1, which is 0 mod n. And so we would basically, it would check out. We will go back to the beginning. And so we have verified this for the base case k is equal to 1. Now for the induction step, we're going to suppose that this holds for a general k is equal to m. Well, in that case, we will have that alpha to the m of a of l is equal to a of l plus m mod n. And now let's prove it for the case n plus 1, where k is equal to n plus 1. In that case, we have phi of n plus 1 of a of l is just equal to phi of m of phi of a of l, but we know that phi of a of l is a of l a of L plus 1 mod n, so this is phi of m, phi to the power of m of a to the L plus 1 mod n, and at this point, applying the induction hypothesis, we get that this is equal to a of a plus L plus 1 mod n, all plus m mod n. But all of this is just equal to a of L plus m plus 1, everything mod n, by the properties of operations modulo n. Now, by proving this, which we have proven this subclaim, we can now notice that if we have, and so now we know that alpha of n applied to a of L for L in the following set, which is 0 n plus n minus 1, intersected with natural numbers, and here we're taking the construction of the natural numbers with respect to the piano accent, where we take 0. This is the starting point, so we're supposing 0 is in the natural numbers, and here we have alpha of n of a of L is equal to it's equal to a of L plus n mod n by the previous fact, but this is just equal to a of L by the properties of operations modulo n. And well, with this we have basically shown that alpha of n fixes all elements, basically a of L for L in that set. And what that means is that alpha of n is equal to the identity permutation, and this proves the theorem. So with this fact, so why did we want to prove this fact? Because it will aid us in the proof of the next quite important theorem. And this theorem tells us some stuff about the order of permutations, because before we proved this fact about order of cycles of length n. But now we will prove a fact about permutations. And in particular, we will say that the order of a permutation of a finite set written in terms of a product of disjoint cycles, we've seen how we can do that in the last video. So if we have a permutation sigma, then we can write it as a product of alpha 1, alpha 2, where they're all disjoint cycles. Well then, if we write this permutation in terms of a product of disjoint cycles, then its order is the LCM, so the least common multiple of the lengths of the cycles. So let's prove it, and of course we will use the last fact. Let's suppose that our permutation sigma can be written as a product of cycles that could be alpha 1, alpha 2, alpha 3, up to alpha m. Okay, so now let's call L the LCM of the orders of alpha 1, up to alpha m. Okay, now notice that since by the previous fact, of course, you know that alpha 1 to the order of alpha m, alpha 1, which is just the length of alpha 1, is the identity permutation, and this is also valid for all the other permutations. And since the L, which is the LCM of all these orders, is a multiple of all these orders, of course this immediately implies that also alpha 1 to the L, alpha 2 to the L, all of these are the identity permutation. Well, why? Because L is basically can be written as some integer k times alpha 1, and also as some integer k prime times alpha 2, and so on. So it's a multiple of all alpha 1 of the orders of alpha 1, alpha 2, and so on. So raising alpha 1, alpha 2, alpha 3, and so on to the nth power will yield the identity permutation. Now, not only we know this, but we also know that since alpha 1, alpha 2, alpha up to alpha m are all disjoint cycles, and by the last video we know that disjoint cycles commute, this implies that this is equal to alpha 1 to the L, alpha 2 to the L, up to alpha m to the L. This is all equal to sigma to the L. But notice that all of these basically cycles raised to the L are just the identity, and so this in total is just the identity permutation. So this implies that sigma to the L is the identity permutation. And by a fact that we have proven in some videos ago, we know that this implies that the order of sigma divides L, which we remember is the LCM of all that stuff. So we can just write it in this way because it's faster. I mean, and so this is basically what we have got so far. So the order of sigma divides L. Okay, but by the very definition of order, then we have that sigma to the order of sigma is the is basically the identity permutation. Or in other words, alpha 1, alpha 2, dot, 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 up to alpha m to the order of sigma is equal to the identity. Now, by using, of course, the fact that disjoint cycles commute, we can write this as alpha 1 to the sigma times alpha 2 to the sigma up to alpha m to the sigma times all of this is equal to the identity. Now, bringing every cycle from alpha 2 onwards to the right by multiplying everything by alpha 2 to the minus order of sigma, alpha 3 to the minus order of sigma, dot, 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 up to alpha m to the minus order of sigma, will yield alpha 1 to the order of sigma is equal to alpha 2 to the minus order of sigma, alpha 3 to the minus order of sigma, dot, 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 up to alpha m to the minus order of sigma. Okay, but let's see what we got here. We got that this permutation, which remember is disjoint with respect to alpha 2, with respect to alpha 3. So we could say alpha 1, I'm using a little bit of abuse of notation because you would say this for, for sets. But let's say that alpha 1 is disjoint. We can write it, again, we're using a little bit of abuse of notation. It's disjoint to all alpha i's for I not equal to 1. So alpha 1 is disjoint with respect to alpha 2, alpha 3, and so on. And thus, it is also, disjoint in the sense that this permutation that is given by the product of these disjoint cycles will also have no effects on the elements that are affected by alpha 1. Because, again, alpha 1 is disjoint with respect to all of these. And then it's also, of course, disjoint. So it basically, the elements that are moving by these things do not affect the elements moving by alpha 1. Also when, grouped together in the product. And what that means is that and now we're saying that this, which is again, for example, suppose that it moves in a practical example 1 and 3, I don't know, in a way like this, and then you have alpha 2 that moves 4 to 5, and then 5 to 6 maybe, and then 6 back to 4, and then you have alpha 3 which moves 7 to 3, for example, and then you have alpha 4 that moves 9 back to itself, and then alpha 5 maybe 9 to 8, and then 8 back to 9. And as you can see, even if we compose these things together, so we product them, still the permutation alpha 1 is not affected by this, no matter if it's these permutations on their own or all of them grouped together in the product. And so now we're basically saying that alpha 1 to the sigma is equal to this. But they cannot be equal unless they're both the identity. Why? Well, because we again said that they have no elements in common that they move. And this means that in order to be equal, they just have to be the identity. And this implies that basically this is equal to all of this, and this is equal to the identity. Okay, but now what we got is that the order of alpha 1, which remember is its length, must divide the order of sigma, and analogously the order of all this permutation here, which we reduced it to a permutation of m minus 1 cycles, must divide, so the order of all of this stuff here, must also divide the order of sigma. And so far we have got, and so now we basically need to proceed by induction. You have to repeat this process for this sub permutation made up of m minus 1 cycles. And so here we did a little bit of, we could say, we did an induction in reverse. We first did the proof for the induction step, and but now we will provide the proof for the base case. The proof of the base case is basically the same to everything that we did here, except that in the last part we have that alpha 1 to the sigma, to the order of sigma, is equal to alpha 2 to the minus order of sigma. And by the same analogous reasonings that we made above, we have that sigma divides, actually that the order of alpha 1 divides the order of sigma, and that the order of alpha 2 divides the order of sigma. And when we reach the case of two cycles, so a permutation made up of 2 cycles, that's where we can say confidently that the order of sigma is the LCM of the orders by the very definition of LCM and by the consideration we made. And of course, then you start by proving it for 2 cycles. Then you will have to suppose that it was true for a general m, and then the proof for the m plus 1 fact would have been done, by the way we did it up here, then using the induction hypothesis for this permutation here. So this actually provides a very untidy proof, but I wanted to give a proof in this way, maybe because it was a little, you could say, more intuitive than just starting out from the bottom. So now you might ask, well, why is this theorem important? And the reason why this theorem is very important, you can immediately understand it when we will provide some example, and we will do it precisely now, because this theorem is very, very powerful. I will show, like, for example, an example could be, consider the following product of cycles, that is 1, 5, 4, then 2, 1, 3, and for example, actually, no, let's make it disjoint, of course, 2, 3, then 7, 6, 8, 9, okay, something like that, actually 7, 6, 8, maybe, okay, and well, the order of this product, all these disjoint cycles, is just 6. You can deduce it immediately by eye. Even if you take a 1, 4, 4, 5, a 6, then 2, 9, then 8, 7, then, I don't know, like 3, 10, 11, like even this, you can immediately tell what the product, or what the order of this is. That is 12. Well, because the LCM of 4, then 2, and 3 is precisely 12. And again, you could provide a lot of examples, and even if you're given a general permutation in the array form that we've given in the last video, such as, I don't know, like 1 gets mapped to 3, and then 2 to 1, then 3 to 4, 4 to 2, and so on, you know, something like that. Well, you could just make it into cycle notation and immediately deduce the order. So that's a very, very powerful theorem. And so, with this said, we now have a very, very powerful theorem to deduce the orders of permutations. And now, the last things that we need to say about permutations is, of course, the important notions of a parity of a permutation. But before we introduce the notion of a parity, let's first prove an important theorem, and that is that every permutation can also be written in terms of a product of 2 cycles. Of course, we have to suppose that the permutations we're taking is of a set of at least 2 elements, because otherwise it would not make sense. So for Sn, where n is the group of permutations, the symmetric group, with n greater than 1, of course, well, every sigma in S of n can be written as a product of 2 cycles. So is prod of 2 cycles. So let's prove it. So we'll start the proof by first noticing that the identity permutation can be written as any 2 cycle to the 2nd power. So any 2 cycle by itself, because, well, we know that the order of a 2 cycle is 2 because its length is 2, and then just multiplying it by itself will yield the identity. So we have an expression for the identity in terms of 2 cycles. Now, also using another theorem, the one that we proved in the last video, we know that every permutation inside of S of n can be written in terms of disjoint cycles. In terms of disjoint cycles in the following way: a1, a2, a3, dot, 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 up to ak, then for example b1, dot, 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 up to bt, then up to c1, c2, c3, up to cs, and so on. And now we can rewrite all of this in the following way. So we can write it as a1, the cycle just a1 ak times a1 ak minus 1, dot, dot, up to a1 a2. Then we can write b1 up to bt as b1, then bt, b1 bt minus 1, dot, dot, up to b1 b2. And we can do the same with c, and let's now see why that works. And well, now we will just give a little bit of graphical intuition. So if we have the cycle that maps a1 to a2, and then a2 back to a1, let's see what happens if we multiply it by a1 a3. So let's see. Of course, notice these are not disjoint cycles, so do not think they will commute. They won't, so the order is important in this case. So we will take a1 a3, then a1 a2. So let's see what a1 a3 does. So it maps a1 to a3. Okay, but mixing these to see more clearly what is going on, let's write them in array notation like this, we're multiplying A1 like maps to A3, then A2 backs to A2, A3 to A1, dot, 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 by A1 gets mapped to A2, A2 back to A1, dot, dot, dot. So A1 here gets mapped to A2, and A2 here gets mapped to A2. So in total we will have that A1 gets mapped to A2. Now let's look at A2 here. A2 here gets mapped at A1, but A1 here gets mapped at A3, so A2 gets mapped at A3. And then A3 gets mapped to A1, and then A4 stays fixed, and so on. And now notice that if we repeat it, I will show you that if we multiply then this by A1 gets mapped to A4, okay, because it's the next one. And well, what happens is all of these remain unfixed, but all of these remain unchanged. But then if you take A3 gets mapped to A1, well, A1 gets mapped to A4. This is basically A1, A2, A2 gets mapped to A3, A3 to A4, and then A4 back to A1, and this goes on. And we can repeat it as much as we want until we could say we finish the entries, and then at the end we just end up with this cycle here. And so I hope this kind of explained why this works. And of course we did it only with the A permutation. It will work just in the same way with the B permutation and the C permutation. And so we have now seen that we can write sigma as a product of two cycles, but that's precisely what we wanted to show, and this completes the proof. So now we know how we can write products of two cycles. So to give, for example, some examples, and to give an example, you could actually just like take the disjoint cycle decomposition of a permutation, which is very, very easy to determine. And of course, if the permutation is not of a set that is 1000 elements long, but if by human, it's easily computable for most cases which you will encounter, in like absolute algebra exercises. Well, this theorem also provides because the algorithmic way to derive it, because well, it gives us the precise way to obtain a two-cycle decomposition from a disjoint cycle decomposition. How? In this precise way that we listed above. So if you have, for example, let's take this permutation here that maps 1 to 3, then 2 to 4, then 3 back to 1, then 4 to 5, 5 to 6, then 6 back to 2. So this in a cycle notation is just 1, 3 times 2, 4, 5, 6. Well, this it's pretty easy to see. It has order 4 by the theorem above. Not only that's order 4, let's now try. So, and also we have a disjoint cycle decomposition of this permutation. Let's now decompose it in two cycles. So the first cycle that we have, we're good because it's a two cycle. So for the second one, we will use this decomposition that we did above. So it will be A1, AK, in this case AK is 6, so it will be 2, 6. Then it will be A1, AK minus 1, so A1, A3, that is 2, 5, and then, well, A1, A2, 2, 4. And now let's see that this product actually yields sigma back. So we'll write this, let's first celebrate these two products here. So this basically just sends 2 to 5, leaves everything else fixed, and 5 back to 2. So that's it. And here, analogously, 2 to 4, everything else is fixed. So the product of these two cycles is basically, well, 1 gets sent to 1, then 2 gets sent to 4, but 4 here gets sent to 4, so 2 to 4, then 3 to 3, then 4 to 2, so 4 to 5 in total, then 5 to 2, and then 6 to 6. So this is the end. Now we need to multiply this on the left by 2, 6, which is everything fixed except for 2 and 6, so 6 to 2. Okay. So what we get is that, well, this is just 1, 1, then 2 gets mapped to 4, but 4 just stays 4, then 3 gets mapped to 3, that is still being kept fixed, then 4 to 5, then 5 to 6, and then 6 to 2. And then multiplying all of this on the left by 1, 3, the permutation 1, 3, which is just 1 gets sent to 3, then 2 fixed, 3 to 1, 4 fixed, 5 fixed, 6 fixed. This yields 1 gets into 1, so 1 to 3, then 2 to 4, the 4 says 4, then 3 to 1, then 4 to 5, then 5 to 6, and then 6 back to 2. And let's see, well, you can see that the permutation is precisely the same one that we wrote above. So this is an algorithmic way to basically split, we could say, permutations into product of two cycles. And now as an exercise, you can try to, for example, write the following permutations, written and also the following cycles into, product of two cycles. So the first one is the permutation of the following three permutations. And also another thing that I want you to ponder about, and that is that the decomposition of a permutation into two cycles is actually not unique. And in order to convince you of that, provide multiple expansions of these two permutations into products of two cycles. So you can try and do that in order to convince yourself that that is actually the case. Now we will prove another important lemma that will then motivate us to define the concept of parity of a permutation. The lemma is the following, and it says that if basically a product of two cycles, B1, B2 up to BR, is the identity, then R is even. In other words, basically R is 0, 1, 2. Well, let's prove it. Well, we start by supposing that R is greater than 1, because of course a transposition by itself, and by the way, I did not say it yet, but a two cycle is also often called a transposition, and by itself is of course cannot be the identity. So if we have like A, B, well, A translates A to B, it cannot be the identity, it does not fix A. And so we will just suppose that, there is more than one, at least two cycles multiplied together. Now, let's suppose that in general, as before, we have B1, B2, B3, up to BR. We will take in consideration the last two elements of this long chain of products. And in particular, if we suppose that, for example, the last element, we can call it, for example, AB, and B to the R minus 1, we can call it CD, then the product can be written in one of these forms. So it is either the identity, if both of them are equal to AB, and remember that's because two cycles have order 2, or it can be equal to AB times BC. But by the products of cycles, AB times BC is also equal to AC times AB. Or alternatively, it could be AC times CB or AB times CD. But again, by the products of cycles, these two are also equivalent to BC times AB and CD times AB. We have now covered all possible, we could say, combinations that we can have of these two elements. And in this case here, we will obtain a R minus 2 product of cycles. And thus, by proceeding by induction, we will get that R minus 2 is even. But if that is not the case, so in one of these three cases, then what we do is we basically replace BR minus 1 times BR with the representation of that product of two cycles on the left, in such a way that we will then have that the rightmost appearance of the element A is in BR minus 1 and not in BR anymore. And so now we're gonna get again two cases. This can either be the identity and get one of the three cases above again. If we get one of the three cases above, then we just do the same and then consider BR minus 2, BR minus 1. Well, by repeating this in the end, we will necessarily end up with a product of R minus 2, two cycles. Why? Well, because of course, if that was not the case, we will end up with the rightmost appearance of the element A on the leftmost cycle. But that implies that A is not fixed, and that would fail the supposition that we made above, that all this product was the identity. So this proves that R minus 2 is even, and thus R is even. And this completes the proof. So this lemma is very useful for the following definition. So actually for the theorem that will basically give the motivation for this definition. And in particular, we call this definition is the parity of a permutation. So we call a permutation, sigma, we call it a even permutation if it can be written as a product of an even number of 2 cycles. On the other hand, if that's not the case, if it can be written as a product of odd number of 2 cycles, then we call it that permutation odd 2 cycles. So, but now what really justifies this definition? So why are we allowed to talk about parity? Like, think about it for a second. So if we have a permutation that can be written as an even number of 2 cycles, well, what really guarantees that then every other representation in terms of 2 cycles of that permutation can also be written in terms of again another even number of 2 cycles? It could as well, we could as well have a permutation that can be written in terms of an even number of 2 cycles, and also we can also write in terms of an odd number of 2 cycles. The result that rules all of this out is the following theorem that says that if a permutation can be expressed, actually I will write it and then skip to the actual assertion, and that is, if a permutation sigma can be written as a product of an even or odd number of 2 cycles, then every decomposition of sigma into products of 2 cycles must have either an even or odd number of 2 cycles. And let's, for example, write it a little bit in terms of equations. So if you have a sigma that can be written as beta 1, beta 2, up to beta m, and for example, you can also write it as, I don't know, like alpha 1, alpha 2, up to alpha L. Well, then we have to have that L is congruent to m mod 1, mod 2. Because, well, if both of them are even, then they're both congruent to 0. If both of them are odd, they're both congruent to 1. So we have that if sigma again can be written as a product of an even number of 2 cycles, then all the compositions of sigma are in terms of even number of 2 cycles. And in the same way, if sigma can be decomposed into an odd number of 2 cycles, then all other decompositions are also in terms of an odd number of 2 cycles. So let's prove it. And so to prove this theorem is really, really simple. All you have to do is notice that sigma, which is can be written as, we will use these two notation that we gave above. Sigma can be written as beta 1, beta 2, up to beta m, but it can also be written as alpha 1 up to alpha L. So now let's multiply sigma by sigma minus 1. This is the identity permutation, but this is the same as beta 1, beta 2, up to beta m times alpha 1, alpha 2, up to alpha L to the minus 1, which is just beta 1, beta 2, up to beta m times alpha L to the minus 1, alpha L to the minus 1 to the minus 1, up to alpha 1 to the minus 1. Okay, but since every 2 cycle is its own inverse, well, why? Because think about it. If you have A that gets mapped to B and then B gets mapped to A, well then, if we invert it, so we want to find an element such that it is the identity, well, by the theorem that we proved above, that every the order of a cycle is its own length, then of course the order of a 2 cycle is 2, which is its own length, and thus it is its own inverse. And so we can write all of this as beta 1, beta 2, up to beta m, then alpha L minus 1, up to alpha 1. But this, by the lemma that we proved above, it basically implies that m plus L is even, so it is congruent to 0 mod 2. But that implies that m and L are either both even or both odd. And that completes the proof of this fact. Now, as a, we could say, exercise, you can try and prove the following facts. So the first one is that the set of even permutations, or of course under composition of permutations, is a subgroup of the symmetric group of order n. And this subgroup in particular is called the alternating group of order n, A of n. Not only that, but also prove that the order of an, so the alternating group, is n factorial over 2. So half of the elements of S of n are even. So with this said, I think we can conclude this video here, and in the next one we will start talking about isomorphisms and homomorphisms.